Hello, in this video, I'm going to sketch the ST, VT and AT graphs for a bouncing ball. We are going to start from the moment the ball is dropped, and we are going to stop the graph at the third bounce of the ball. We are going to neglect the air resistance. We are going to assume that the collision with the floor is elastic. This means that no KE is lost during the collision with the floor. Let's take upward to be positive. As usual, I will encourage you to pause the video now, sketch the graphs all by yourself first, and when you are ready, join me again. As usual, I will start with the VT graph because it's the most interesting graph. We're going to start from the moment the ball is dropped, so we are going to start with a velocity of 0. And as it falls, it's going to speed up. Since we have taken upward to be positive, our velocity is going to become more and more negative. It's going to be a straight line graph because the ball is free falling at a constant rate of 9.81 meter per second square. Let's take this to be the instant when the ball makes contact with the floor. So this is the maximum downward velocity of the ball. Now, something interesting happens here. During the collision, in a very short amount of time, the velocity of the ball is going to switch from maximum downward velocity to the maximum upward velocity. So it's going to be an abrupt change in the velocity. And it's going to switch from maximum downward to maximum upward. These two speeds are the same because we have assumed that the collision is elastic, meaning there's no loss in KE. So this must mean that the ball will rebound at the same speed at which it collides with the floor. So now the ball is going to make its way upward, and as it rises, it's going to slow down. It's going to slow down until its speed becomes 0, and that's when it's at the peak of the bounce. Now it's very important that you draw these two lines to have the same gradient. This is because whether it's falling or whether it's rising, the ball is undergoing constant downward acceleration of 9.81 meter per second square. So the gradients of the VT graph along here and along here must be exactly the same. Okay, from this point, the ball is going to make its way down again. And so it's going to accelerate down again at the same rate. So it's going to be a continuous straight line. And then it's going to hit the floor again here. And then the cycle repeats itself. Okay, now that we have the VT graphs, let's work out our ST and VT graphs. The ST graph is going to look like this. The gradient of the ST graph is of course velocity. So let's quickly check whether this tallies with our VT graph. So the gradient of our ST graph starts off being very positive and slowly decreases to 0. And this tallies with the velocity starting being maximum positive and decreases to 0. Past this point, the gradient of our ST graph becomes negative and become more and more negative. This agrees with our velocity starting off from 0 here, becoming negative and more negative. Let's now move on to the acceleration time graph. Now during these sections of the VT graphs, the gradient is always the same. It's always negative 9.81 meter per second square. This will mean that our AT graph is a boring horizontal line for most of the time. However, the gradient of the VT graph is not negative 9.81 during the bounce. In fact, you look at here. The gradient of our VT graph here is a very sharp positive gradient. So to reflect that, our acceleration time graph should have very positive spikes where the bounces are. Now, do realize that when the ball collides with the floor exerts a very large upward force on the ball for a very brief duration of time. So, whenever the ball is airborne, it doesn't matter whether it's on the way down, on the way up at its peak, as long as it is airborne, the only force acting on the ball is mg, which gives it a downward constant acceleration of 9.81 meter per second square. However, during the very brief duration when the ball is in contact with the floor pushes the ball hard upward, giving the ball a net force that's upward. So now we understand why the acceleration is positive here, because the net force is upward, and so the acceleration is also upward and positive. Now this positive acceleration in fact is going to be a very large acceleration, because how else can you slow down the ball, bring it to rest, and accelerate it back to its original speed in such a short interval of time? With this, I hope you understand the spiky looking acceleration time graph for a bouncing ball. Ta-ta!